Hello and welcome on behalf of NTI Audio. Today we want to present to you three special features of the FX control software: the regulators, the calculation items, and the definition and application of tolerance limits for a passed-failed test. My name is Markus Becker. I'm moderating this webinar and I'm assisted today by Greg Schmiedle, our product manager and Flexus specialist. On the left-hand side, you see the topics that we have prepared for this presentation. After a short overview, we will explain to you the concept of the regulators, of the calculation items, predefined calculation items or customized ones. We will also present to you the definition and application of tolerances, passed-failed limits, whether they are based on a golden sample or on a bunch of collected result curves. Actually, these three chapters of our presentation will be covered mainly by a practical presentation. After that, I will summarize the key topics and add some more hints and tips. I expect that this presentation will last about half an hour. Well, to understand the demand for these three features, let us assume you want to verify the performance of a microphone. For that purpose, you need, of course, a speaker that replays the test signal. But as you know, every loudspeaker has its own frequency response. So you're interested in not in the frequency response of the loudspeaker, but of the microphone. So you are looking typically for a solution, for a way to get a flat frequency response from that reference speaker. How can you do that? Well, one approach is to somehow invert the frequency response of this speaker and feed the corresponding signal to it so that you get a flat frequency response, acoustically flat frequency response here that is heading towards your microphone under test. So this procedure is, of course, a rather complex one. It would be rather cumbersome to do that manually. And for that purpose, we are offering a regulator that assists you to adjust the generator level, so to get a certain sound pressure level here at the output of your loudspeaker and to equalize the test signal. Another regulator would be to optimize the analyzer input range, in other words, the sensitivity of your audio analyzer in order to achieve maximum precision and accuracy of the measured results. Well, next step could be that you are interested in some special result data. Of course, the audio analyzer provides a wide range of standard measurement functions, level, distortion, phase, and so on and so forth. But maybe you're interested in specific results that are not provided by this standard range. For instance, a calculation of the current by using the voltage and the resistance. It's just a very simple example, can be a more complex one. Maybe you want to know the resonance frequency of a frequency response, or you are looking for an linear interpolation of a curve. There are many specific demands that are typically not covered by standard analyzers, by standard measurement functions. So here we need a way to establish a calculation formula and apply it on the acquired test results in order to get your customized measurement. And of course, or actually in FX Control, we are also offering a range of predefined calculation items that are typically used in practice. You're going to see that in a minute. And the third part of your daily work is typically the definition of a passed fail test, because you want to know whether your device under test now is good or is it bad, does it meet the requirements or not. So for that purpose, it is quite apparent that you need to, first of all, build the foundation of such a test in terms of knowing what is good, what is bad, to collect good samples, maybe bad samples, to then define the tolerance band and to apply it, of course. So this procedure of looking for good, bad samples, for defining the tolerance limits, can be supported with a semi-automated procedure, or it can be done manually. I'm going to show that to you as well. Well, that brings me already to the practical part of this webinar. I have here an FX100 on my desk, which is connected to the PC. The FX100 has a built-in SiP module, which is a power amplifier. The power amplifier drives this loudspeaker here, and I have an input switcher option for the microphone and the other input. Here, actually, in addition to this acoustical test setup, I have also an amplifier connected to my FX100. So let me swap over to the FX Control software. And when we start setting up a test, we always recommend to virtually build this setup with this hardware and wiring view. So here in that case, for instance, I would add a loudspeaker connected to the output of my SiP module. I connect the input of the module to my generator, channel 1, and I add a microphone, as I have it here on my desk, connected to input channel 1. So this virtual representation, sorry, I have connected that to the wrong output. This is the one. This is the correct one. You see that here now it has turned green. That shows me that now the link is correct. Well, coming back to this microphone, if you click here on the microphone, you see here in the properties, we have automatically activated the microphone supplied 48 volt phantom power, and we can enter the correct sensitivity of the microphone, which is of course crucial to achieve to measure the correct sound pressure level. Well, having done that, we can swap to the worksheet view, and here I'm going to show you now, first of all, a very simple regulator, and that is, for that purpose, I will pull my generator output level panel here on my worksheet. I activate the generator by clicking here on that button. Now it's on, and I add the generator level regulator. I confirm. So what does this regulator do? It allows me to adjust the output level of the loudspeaker, which is measured by the microphone, of course, to a certain level. Let's assume, for instance, I want to achieve 180, sorry, not 100, just 80 dBSPL. So I select the unit dBSPL and I replace this value by the 80 dBSPL that I want to achieve. Now I click on Run. And with few iterations, the system finds out that at minus 13.37 dB volt generator level, I will get the 80 dBSPL. I apply, which means I copy this value here to the generator output. And in order to verify that, I can open a measurement panel, meter level channel 1. Okay, see it already here. So by repeating this test, by the way, I need, of course, also to adjust the unit of the measurement panel. So by repeating the test, you're going to see we have really achieved the 80 dBSPL. However, this regulator is not limited to level. It can also adjust a certain THD, for instance. Show you that. So I add a THD measurement panel to show you the impact. And I go back now to my regulator, look at the properties. Instead of level, I want to now adjust a certain THD. 1% is fine for me. Now let's start that process. Maybe you heard it in the background. With a few iterations, the system has evaluated 0.48 dB volt as the generator output that results in a THD at the loudspeaker output of 1%. So that was a very simple example. Let us now show you a more complex one. For that purpose, I add another sheet here. And this time we want to equalize the output level of our loudspeaker. And for that purpose, I need another regulator. I need the generator equalization regulator. So I click on here, I confirm, and it opens this panel here. You can see it here. Now, a few adjustments I have to make first. I have to decide whether I want to use a step sweep or a glide sweep. I go for the glide sweep. I have to adjust the bandwidth in which I want to equalize it, the loudspeaker frequency response. So I go from 300 Hertz to 3 kilohertz, which is appropriate for my sample here on my desk. I can adjust the duration of my glide sweep. I go down to 1 second to speed it up. And again, I have the tolerance the target. Let's go back to the dBSPL unit and let's say 80 dBSPL. And the last thing I do is I'm going to activate the smoothing. This means that the measured curve will be smoothed in order to quickly get a reasonable result. So I just activate that to the third octave smoothing. Now I can click on the run button, and what you're going to see now is that the system will try to find an appropriate weighting here in the generator. This is the frequency response of the generator, and the target would be to get a flat frequency response down here at the loudspeaker. That is the incoming signal from the microphone. So I start the procedure. So you can see with a few iterations, the system has found the correct weighting of the generator output level in order to achieve this very nice flat frequency response at our loudspeaker. So here you see the beauty of this regulator. It really takes away a lot of work from you in order to get this setup, to establish the setup. Now, coming briefly back to this smoothing that I've already mentioned, the smoothing actually is already a calculation that is done by the system. So it receives the raw data from the microphone, the measurement data, and it smoothens it. So this is already a calculation, and I'm going to show you more about this calculation items in a next step. And for that purpose, I open a new project. And this time we want to measure the frequency response of the amplifier that I have connected, and in a second step also the noise level, but let's start with the frequency response. So I drag and drop here the generator level again to my worksheet. I adjust the level to -10 dB volt on both channels. I activate both channels, and I add a glide sweep level measurement. Here we have channel 1. And I can also add a channel 2. I drag and drop channel 2 over this existing graph, so that will show me both results on one graph. Here I have dB volt. Here I have, that should basically work. Let's see. Well, let's do a measurement. Yeah, you see the two curves, green and pink, the two channels. You see there is a noticeable difference in the frequency response of the two. And the other thing we have to state is typically a amplifier is not defined or not represented with an absolute frequency response. Normally you would use a relative frequency response. You want to know the relative frequency response versus the result at 1 kilohertz. So this is not what we see here. Apparently we need to establish this special measurement, and fortunately we have a predefined calculation item. It's called relative response. When I click on here, you see this panel opens. I can name it number 1 for channel 1. I say this relative response shall use the glide sweep level channel 1 measurement data and put it into relation to 1 kilohertz. I confirm, and you see immediately the result panel shows me this the calculated relative response. I can add also the channel 2, again, relative response. Now we have number 2. As input, we are using glide sweep level channel 2. Same 1000 Hertz as reference. I confirm, and you see, by the way, down here, these are these 2 calculation items I have just created. Now I drag and drop the second one to this graph, and you see now the 2 curves again, the green and the pink representing the 2 channels. Well, maybe in a next step, you want to know the difference between the 2 channels. And here, actually, we have to do that manually. There is no predefined calculation item for that, but it's very easy to do that. We click here on the plus symbol, opens this panel. We call this calculation item difference. This is now will be a customized calculation item. We add 2 parameters. First, glide sweep level channel 1, and second, glide sweep level channel 2. So here you see the 2 measurements represented by these variables, x1 and x2. And the last thing we have to do is just find the calculation that shall be applied, x1 minus x2, select the unit in which the result shall be displayed, confirm, and here we have now the graphical result, the curve that represents the difference between these 2 curves. You see here the difference was very small, getting larger at the higher frequencies. You see here close to 0 in the beginning and then getting larger at higher frequencies. So that is a simple example of a calculation item. Now let us take a look at a more complex one. And for that purpose, again, I'm going to create a new project just to start from scratch. Now I want to determine the noise floor of my amplifier. I start again with my generator level and I let it muted. So in a first step, I would measure the spectrum of my analyzer output. So I select FFT channel 1. Here, let us do a measurement. Well, you see, when the input of the amplifier is muted, the output creates this signal. So there are some distortions, whatever, here in the upper frequencies. And let us say we want to take a closer look at the behavior of this spectrum of this amplifier. So the first thing we may want to know is the wideband level, the wideband noise level. So for that purpose, we just add the level measurement of channel 1. This will be this panel here. So that's the wideband level. It will afterwards switch to dB volt as soon as we have executed them. Let me just do it. So we test. Now this is now the wideband level of our amplifier output. But now we are more interested in getting specific areas in the spectrum, not just the wideband level. We want to define maybe some bands, frequency bands in which we are interested in the level. And for this, to achieve this, we definitely need another calculation item. So I click here on the plus button again. I call this calculation item calculated noise. And my input parameter is the measured FFT channel 1. So now I have my spectrum levels, and I'm looking for the formula to calculate the level, the corresponding wideband or limited band level of it. How do I do that? So now we have to take a brief look on the mathematical side, and I want to show you that here we are looking again on the calculation of a band limited level out of an FFT spectrum. And we get that in 3 steps. The first step is we have to convert the FFT level, which is expressed in dB, into a linear unit. In a second step, we can calculate the RSS. RSS stands for root sum square. That is comparable to the root mean square, which you probably know. Root sum square is the correct choice for the FFT analysis, for the bin calculation. And third step, convert the result, which is linear, back into the logarithmic scale by converting it into dB. And this is the formula that it does it. We start here with the FFT level, our measurement result. AdB stands for anti-dB, so the conversion from dB into a linear unit. Now in this brackets, we have the linear result. We can calculate the RSS, the root sum square of this result. And the last step is we convert it back into dB. So all we need to do is to copy and paste this formula into our FX control calculation item. So let me do that. dB of RSS of AdB of X1, my measurement result. That's too much here. Okay, dB, RSS, AdB, or from inside out, first conversion into linear, RSS, and conversion into logarithmic. The result shall be displayed in dB volt. I confirm. This is my result panel, and you already see the 2 results are very close to each other. So the wideband measurement, which is provided by the Flexus analyzer anyway, and my calculated result, calculated from this individual bins here from my spectrum. But as I said, I want to go one step further. I want to now calculate the noise from a limited band. How can I do that? Well, I have to drag and drop the FFT properties here on my worksheet. Just to make that smaller. Well, these are the FFT properties. And let me amend just 2 things here. I change the size of the FFT, and here the detector type means whether you want to base your calculation on the maximum peak values of the bins in that FFT spectrum, or whether you want to use the power. In my case, I want to use the power. So now I am free to edit the frequency bandwidth. Let's say I want to look at a band from 5 Hertz to 20 kilohertz, because anything beyond 20 kilohertz I wouldn't hear anyway. So that is my band limitation, and as soon as I repeat the measurement, you can see here the upper result, the wideband noise level is the same as before, but now the calculated noise from this band limited spectrum will be much lower, because I have now excluded these upper harmonics or whatever it is in that spectrum. So this is an example on a maybe more complex calculation item under FX control. Well, now let us take a look at the third part of our presentation, the tolerance, the acceptance limit definition. And I start with a simple example. Actually, I'm gonna select a predefined project, one that is the same as we did in the very beginning. Here we had our level, output level with the regulator for the 80 dB SPL. Let's redo that measurement. Click here to dB SPL. So here we see we have the 80 dB SPL. Now let us say we want to make sure that the in a practical application, the measured level is always between 78 and 82 dB SPL. So these are the low and the high limits that shall be applied on our measurement, on our test run. Furthermore, I'm going to edit the scale of my bar graph because I know it is something, it will always measure something between 70 and 19 dB SPL, and redo the test. And you see now blue was my measurement result, or here numerical. Green is the acceptance range. So green is my tolerance area. But I can even add another measurement. Let's say the frequency of channel 1. That shall be 1 kilohertz. So I can here edit the acceptance criteria for the frequency. Same as the scaling. Sorry, it shall be. Okay, measure. Here you see the measured frequency and the acceptance range. You see the green color indicates to me that I have met my criterion, but I can also add a passed fade indicator. But just need to select here the corresponding measurement. You see this passed stands for this measurement. And if I want to add another one for the frequency measurement, so I'd select here the frequency result. So that stands for the frequency measurement. And maybe you are even interested in a combination of these two results. You want to have one panel that shows you whether all these sub-tests, all of them have passed the test. So for that purpose, we need another predefined calculation, the overall passed failed. And all I need to do is to add the corresponding measurements, the frequency measurement and the level measurement. So this would be my overall result, and I'm gonna just show you the effect. I'm gonna start now our continuous test, a repeated test of this frequency measurement, or frequency and level measurement, and I'm gonna manipulate my test setup so that you're gonna see sometimes the level will fail and you see the result straight away. So you see, as soon as one of the two drops out, the overall result will be failed again as well. So that was a simple example of a passed failed and tolerance definition. Let me show a more complex one with a graph with a frequency response. I have prepared that already. So I open it here. So here you see the generator level once again. Here we see the frequency band of the glide sweep I'm using. Here I have another regulator, the glide sweep range. This is a regulator that helps me to determine the optimum input range, the optimum sensitivity of my analyzer. Well, all I need to do is just click on this button and the system will determine the optimum input range. Down here we see two graphs. On the left-hand side is a graph that always shows the last measurement result, and on the right-hand side with the yellow background is a collection of all measurements that I have executed. Well, this first glide sweep was not a measurement. It was a part of this regulator procedure, so we can forget about this result. But let us now do a couple of measurements. You're going to see the effect on these two panels, on these two graphs. So that was a couple of tests. You see here on the left-hand side, as I said, always the latest curve. Here on the right-hand side, here you see it also. We have executed 4 cycles. The first one was the one with the regulator. You remember when I click on it, you see it's blue. You can highlight it, and I can delete that curve because I don't want to have it in my results. But now these are the 4. Could be, for instance, 4 samples that I have measured, and they shall be now the base for my past fate decision. So how do I establish the tolerance limits? I just click here on the Create Calculation item. The panel opens. I can, for instance, say I want to have all the maximum points of all these curves, of every curve. What is the maximum of all curves together? And for instance, I could say I want to add a headroom of 60 B, or I can say take the minimum minus 60 B, or I can take the mean. I have a couple of possibilities to build the foundation, the base for my tolerance limits. Actually, I already did that. You see that here, the maximum glide sweep and the minimum glide sweep level of these curves, and that is the reason why you see also here the past results. So the system has already compared these measured curves against these limits. Here on the left-hand side, the tolerance band is even visible with this green shaded area. How did I establish that? Show that very quickly. I click on the panel, I look at the properties, click here on Edit Data, and you see here now my tolerance band, which was manually edited. Just right-click, you can add points, you can shift them around, so you can graphically define your tolerance band or even do it numerically via a table. Well, let me get back to my PowerPoint presentation. Very briefly summarize the whole procedure. We started with the regulator. The regulator allows me to weight the generator output in a way that it compensates for the behavior of the device under test, so that I achieve a flat frequency response here as the output. Next step would be to execute different measurements and use the results for a calculation of a new result. I can even add external information, external data into that calculation. Then the outcome could be, for instance, these curves. I'm executing a couple of measurements, collect the curves in order to build a tolerance band for the past fate test. My last slide here, the overview over the regulators that are available. I showed you 3 of them, the generator level, the glide sweep range, and the generator equalization. Here, the selection of predefined calculations. I did not go through all of them, but that would lead too far. Remember, we can also establish our own customized calculations. And if you want to know anything in more detail about that, please take a look at the FX Control help file. It offers a wide range of information with examples, how you can establish, how you can use these calculations for your application. Well, that brings me to the end of my presentation. Me from my side, thank you very much for your attendance. I hope I was able to answer most of your questions, and I would be, of course, happy to welcome you at one of our future webinars. For the time being, have a good time, stay healthy, and bye-bye.